Question 8. A car traveling at some unknown speed slows to 72 kilometers per hour over a distance of 50 meters in 2 seconds. A. Determine the acceleration of the car. B. Find the initial speed of the car. C. How much further will it travel before it stops if we can assume the same acceleration throughout? This question, ladies and gentlemen, is a Section A, Section B problem, because here's what we got going on. So we know that the car is, and the key word is this, it is traveling at some unknown speed and then slows to 72 kilometers per hour. And what that implies is the unknown speed happens first, all right? So this would be a V1, where this would be a V2. We know that that occurs in a distance of 50 meters and that occurs in 2 seconds, all right? So these all are related to each other. Now, how do we know that this is a Section A and a Section B problem, not just a single section problem? It has to do with what happens here in Part C. So in Part A, it says determine the acceleration of the car. Well, that's all relevant to what's happening over here. Find the initial speed of the car, which is what we're looking for over here. That's all relevant in this first section. But the key is here is it asks specifically how much further will it travel before it stops. Assume the same acceleration throughout. So what we've got here is that this is our Section B that we're referring to here. So Section A has everything to do with these numbers up here. Section B is related to Section A based on the acceleration of the car. And of course, there's one other thing that is in common, is that the speed at the end of Section A is the same as the speed at the beginning of Section B. All right, so let's break this down. So what I'm going to do is I'm going to use green for Section A, and I'm going to use blue for Section B. So what we have in Section A, we know the following things. We know that the VA2 is equal to 72 kilometers per hour. Now we need to convert that to meters per second, and that works out to 20 meters per second. The next thing that we know is we know that the distance that we travel in Section A, technically it's a displacement because we're moving forward, but that's 50 meters. And we know the time for Section A is 2 seconds. All right, so now let's talk about what we know for Section B. So in Section B, what we know is that the beginning speed of Section B is the same as the ending speed of Section A. So that is also 20.0 meters per second. The thing we know about Section B is we know that the final speed is 0 meters per second. And we know that because of the key word right here, it stops. All right, so now let's go into our solution section. And we know that we have accelerated motion. Actually, let's continue the RTF first of all. In Section A, we're looking for the acceleration of the vehicle. In Part B, we're looking for the initial speed of the car. Specifically, we're looking for VA1. And in Section C, it's asking us how much further it travels, right? And further, that is a measurement of distance. So what we are looking for is the distance in Section B. All right, so first of all, let's draw a diagram of the situation. So we know that the vehicle is continually slowing down. So to draw this, I have to do it a sort of a low-tech way, all right, because I can't do the dashed lines directly, but we do know that it is slowing down. So what we can do here is the lines get increasingly shorter together as it slows down. That's probably good enough. We can probably get rid of the rest of that. All right, so the first section here, this is our Section A, and then the second section here, this is our Section B. What we know are the following things. So again, I'd like to put the same given information that we have up in the given section. I'd like to also put it in the diagram as well. So I know that my VA1 is unknown. My VA2 is equal to my VB1, and those equal 20 meters per second. And my VB2 is equal to 0 meters per second. The other thing that we know is we know how far we traveled in Section A. We know that the distance or displacement in Section A, and the reason why we can say distance and displacement is because they're both traveling in a straight line and there's no change in direction. So the distance and the displacement do behave in the exact same way, but that is only because they are traveling in a straight line and there is no direction change. So the dA is 50 meters, And the time in section A, I believe, was 2 seconds. Everything to 4 sig figs. All right, so the next question is, where do we go from here? Well, we know that we're looking for the acceleration. So what we're going to do is we're going to make our list of the variables that we have. All right, so when we make the list of the variables that we have dA, VA1, VA2, acceleration in section A, and the time in section. Okay, so let's see. Well, let's fill in the information that we know. We know that this is 50 meters, all right? And that is given, so I'm going to put a green check mark for that one, all right? And the reason why we're putting a green check mark is we know that there's no possibility for error. We are looking for the following two things, ultimately. We're looking for the acceleration in section A, and we're also looking for the initial speed in section A. We know that the final speed in section A is 20 meters per second, and that is also a given. Finally, we know that the time is 2 seconds, and that is also green because that is given and there's no chance for error on that. All right, so now what we have here is we have 3 out of the 5 kinematic parameters. Since we have 3 out of the 5 kinematic parameters, that means that we have enough information to solve for everything. So the first thing we've asked to solve for is we've asked to solve for the initial, my apologies, not the initial speed, but the acceleration of the vehicle. All right, so that's what we're going to do. So we're going to solve for, and we're going to find acceleration in section A. So to find the acceleration in section A, we are going to require a formula that has acceleration, VA2, dA, and TA. And from our list of equations that are on the board, this would be equation number 3. And equation number 3 is dA is equal to VA2 TA minus 1/2 AA TA squared. Okay, so again, we're looking for the acceleration, so we must isolate for acceleration in section A. My workflow, in my opinion, best practices is that since this is negative, I'm going to bring this entire term here to the left-hand side. At the same time, I'm going to bring this term to the right-hand side. So this gives me 1/2 AA TA squared is equal to VA2 TA minus dA. So when we isolate for this, we need to get A by itself. So we need to get rid of the 1/2 and we need to get rid of the TA squared. Well, the first thing, the opposite of 1/2 is multiply by 2. All right. So there's multiple steps. So we've got 2 bracket VA2 TA minus dA. And don't forget the brackets, those are key. And then of course, to get it by itself, this becomes 2 VA2 TA minus dA all over TA squared, which equals 2 bracket. Our VA2 is equal to 20 times 2 minus 50, close bracket, over 2 squared. I'm dropping the sig figs for this part because it does make it a little bit easier to work. So that's 2, okay, so 2 times 20 is 40, minus 50, that is negative 10 inside there, over 4, which gives us negative 5 meters per second squared. And that is our rate of acceleration, all right? Negative 5 meters per second squared. All right, now, of course, the issue about this, and always wary of this, because since this is a calculated value, it has the potential for error in it, all right? It does have the potential for error in it. So next, the next thing we're asked to find is VA1, all right? Now, technically we have the acceleration, but if we can avoid using the acceleration value, it's best practices. The reason being is that this does have a potential for rounding error or actually just a mechanical error. So we should avoid it if we can. If we look at this data, we already have enough information as it is, so we can solve without it. So we're going to avoid using the acceleration. We're just simply going to use the formula that we have that has dA, VA1, VA2, and time in it. And the version of the formula, the only formula that we have that has all of those things, is V2 is equal to VA plus acceleration times time. So let's take on that next. All right, so put another dividing line here. Let's be consistent with coloring. All right, so now next is we are going to find VA1. All right, so we're going to use VA2 is equal to VA1 plus A times T. We are now going to isolate for VA1. To do that, I'm going to bring the last term over to the other side. I'm going to get VA2 minus AA times T, and that's equal to VA1. Rearranging, I got VA1 is equal to VA2 minus AA times T. I realize I forgot to put the subscript A on that, so to correct that, right? Now we can substitute in. And of course, it looks like I forgot the subscript as well. There we go. So VA2 minus acceleration A times time A. Substituting in, our VA2 is equal to 20 minus negative 5. So the negative and negative will make that a positive, times 2. So that's 20 plus 2. So that's negative, negative. That's going to make that a positive. 5 times 2 is 10. So our VA1 should be, to the correct number of sig figs, 30 meters per second. All right, so that's what we've got. So we've got our VA1 is equal to 30 meters per second, and I forgot, acceleration A is equal to negative 5 meters per second. Got a little inconsistent with my coloring here, but I think we all get the point. All right, so now, next, we've solved everything that we need to find for section A. The next thing we're asked to find is we now have to find the distance or displacement in section B. So let's take that on. Right? So we'll put a little dividing line here. Next, we have to find displacement in section B. So I'm going to make my given list for section B. So for section B, dB, VB1, VB2, acceleration in section B, and TB. All right, so first of all, this is what we are trying to find. VB1, we know the value for VB1 is 20 meters per second because the speed at the beginning of section B is the same as the speed at the end of section A. And this one we give a green check mark for because we know this value to be an exact value, and that was given. VB2 we know is 0 meters per second because we know that it comes to a stop, and that is also green. The acceleration, well, the acceleration, as stated earlier in the question, is the same throughout, so that's going to be the same acceleration as section A, makes it negative 5 meters per second. However, with caution, we know that value, but I'm using this orange, this amber color, to indicate that to proceed with caution. The reason why we proceed with caution is because this value potentially could have error in it. So the final thing, time for section B, that is unknown. In this particular case, we have no alternative. We must use this value for the acceleration in our calculations. Even though that there is a potential for error in it, we have no choice because we have no other values to work with. So now we're required to solve for dB, and we need the one formula, the one kinematics formula that does not have time in it. And if you recall, that would be equation number 5, and that is, a little dividing line there, and that equation is VB2 squared is equal to VB1 squared plus 2A of section B times D of section B. Now, when we rearrange for what we're looking for, again, we're trying to solve for dB. So we have to remove the VB1 term, bring it to the left-hand side, and then we have to get rid of the factors 2 and AB. So that becomes this, VB2 squared minus VB1 squared is equal to 2A section B times D section B. The opposite of multiplication is division. So we've got VB2 squared minus VB1 squared all over 2A, and that is equal to dB. So dB is equal to, substituting in, VB2 is equal to 0 squared minus 20 squared over 2 times negative 5. Now here's what we have to ensure. We know that the vehicle is moving forward, so the dB should ultimately be a positive number, and it's going to be. Because if you take a look at the numerator is going to be negative because it's 0 minus, and notice only the 20 is in the brackets, not the negative. So squaring will not affect the negative. If the negative was inside the bracket, the negative would be affected, but it is not, so it is not. So 20 squared is equal to minus 20 squared is equal to negative 400 in the numerator, because obviously 0 squared is still 0, over negative 10. And this gives us a value of 40.00 meters. And that is